నేను దీంట్లో నైనే కదా స్టార్ట్ చేశాను. రిఫ్రెష్ చేశారా? రీసెట్ చేయమంటారా టెస్ట్ సెంటర్? ఇప్పుడే ఒకరు జాయిన్ అయ్యారు. హలో, ఒకళ్ళ చూడండి ఒకసారి. Hello, am I audible to you, everyone? Just please respond, Nana. My voice is audible. Is my voice is audible or not? No. Okay. Okay. No. Let me start here. Unit 2. Actually, in the last class, we just introduced a brief introduction about bipolar junction transistor. Now, we are going to discuss the transistor configuration. One second. Hello. So, a brief introduction about BJTs. Now, so what are the topics we are going to learn in our unit 2? Next slide will be our what we're going to learn about bipolar junction transistor. First, let me learn about our. I'm going to share your my screen. So next, so these are the objectives of our unit 2. So let me first discuss about the basic structure of bipolar junction transistor, why it is called bipolar junction transistor, why it is having two junctions, and why we call it as a bipolar. So expand, we are going to analyze the basic transistor biasing, like our PN junction diode. We have applied forward bias, reverse bias, and what are the currents, so in forward bias, and what is the current named as in reverse bias, and the applications, all those things we have learned in our unit 1 PN junction diode. So in our session, so we are going to learn about the basic transistor bias. So how many types of biasings are available, and how based on the biasings of your two junctions, so what are the regions they are operated, and why we go and those regions, how the transistor is acting like a so will it is acting like a amplifier, will it is acting like a switch, or will it amplifies the AC signal, will it amplifies the DC signals. That all the things we are going to learn in a second concept. So the second concept is our analyze of a basic transistor bias, as well as the operation of your basic transistor. We have two types of transistors, and each one clearly I mentioned the working principle of each transistor configuration. So thereafter we are going to learn about the characteristics. So the third concept is here parameters. What are the parameters we have in our transistor in analyzation, and the characteristics of transistor, based on the characteristics where you can apply those transistors. So for three configuration: common base, common collector, and common emitter configuration. So now simple logic. So this is a tap which is having a valve, and which is having a inlet, and which is having an outlet. So let me take about the inlet is the port 1, and the outlet is the port 2, and the wall is the port 3. Okay, so we have three ports now here, based on the control or the physical energy what you apply, or the physical force what you apply on the wall, can control the flow of current which comes out from your tap. So we have, if we close the tap, then we have a we doesn't have any flow of the water or any flow of the gas. So now if we we fully open the valve, then we have a flow of a fully flow of a water we need it. So this is a simple concept. Now let the port 1. So now this is the practical application, actually practical example. Now we will just interpret that to theoretical concept or electronics. So now here this is an example. Now your transistor is an example for a semiconductor device like your PN junction diode. Now where you have only one junction in PN, whereas in bipolar junction you have two junctions. So we have three regions. So hence here we have given the three ports. Now first port is the inlet, second port is the outlet, and the third port is the your wall. So let's interpret that to your device. So inlet is your emitter, outlet is the collector, wall is the base. So now we are applying in order to have the flow of water or a gas from the tap. We are going to apply the physical energy on the tap. This is manner. So now the third port is your base. So when I apply a proper electrical energy instead of physical energy, we are going to apply electrical energy on the base. So based on the magnitude, how much you apply the energy, electrical energy on the base, so it can control the operation of the transistor. So it can give the heavy amount of current and it doesn't give the current. So zero current will get it as well as the saturated current. So only it is operated, don't think that only it is operated under two regions. So it is operated under saturation, which have a large amount of current, and whereas we have in a cutoff region where it doesn't have any flow of current. So that will be treated as a logical zero in binary format or digital in digital circuits. Mainly your transistor is functioning like an amplifier. So we're going to utilize your BJTs in an analog applications and as well as for digital application. In digital applications, we're going to utilize these the transistors which are operated only in two regions. One will be in the saturation, the other one will be your cutoff. So saturation state will give logical one, cutoff state will give, it can be used as a switch. So saturation state is on switch and cutoff state is of transistor is a off switch. So next in analog applications, so in order to amplify the analog signals, for example in your public addressing systems, if you doesn't have any amplifier, so our voice will not reach to a longer distance. Hence, we need one amplifier, and in that amplifier, our audio signal first it is converted using a mic. So your sound signals are converted into electrical signals. Thereafter, that electrical signals are being applied as an input to the transistor, where that transistor is acting like an amplifier. And that amplifier, which is a transistor, which is operated in active region, and that can amplify the voltage levels. It is amplified by that voltage level with the sufficient voltage levels. The smaller signals are now amplified, then that will be given to the loudspeaker. So with that, we can transmit our audio signals which are in the range of 20 Hz to 20 kHz to a longer distance. So these are the some examples or the practical applications of a transistor. This is the important thing why we are using or why we have to prefer the transistor in a practical or a real world applications. So to manufacture your computer, so where we are going to upload our software, we're going to execute the programs. After that, we'll get the output. But internally, what is the happening in a computer? So it has to be converted into first the high level language is converted into so low level language or a machine level language, where that machine level language consists of zeros and ones. Once those instructions are executed by the microprocessor or a microcontroller, then only will get your required outputs. So in those applications also, in digital applications like to construct your digital your systems or your computers, or we can also control your traffic lights. So using this transistor, which can function like a switches, which can give a zeros or ones. So these are the simple brief discussion. Now the same operation what I just discussed about the water pump. So that I explained here. So a proper applied base to emitter voltage. A proper applied base to emitter voltage or the electrical energy can transfer the amount of current from emitter to collector. Then only we have the collector current which can be obtained here. So why we have named this as a emitter base collector? So this emitter region can emit the free charge carriers, and the collector region can collect here those free charge carriers which are transferred from emitter, and then that will be diffused into your base, and then that will be transferred to the collector. So from that collector output terminal we will collect the amount of current. Is it clear everybody, this concept? Please respond now. Is it clear everybody? Do you have any doubts till this? Do you have any doubts? Clear? Is it clear? Right. Next I'll move to the next slide. So now the applications, real world applications, older over, not just I said a simple, I took a simple application and yes I described about that. What is the need of the transistor? Yeah, real world. Next I'll move to the next slide. So in my next slide, I have the transistor structure. Actually, in last class itself we have completed it. So I said this is a 3-terminal bijunctional 3-region transistor. Why it is called transistor? It will transfer the amount of current from low resistance to high resistance. It will transfer the amount of current from low resistance to high resistance. Hence, it named as transistor. So bipolar means, so we have two polarities. One is the positive polarity, the second one will be the negative polarity. So these positive charge carriers we also have the negative charge carriers. So both charge carriers can compute the total amount of current in a transistor. Both positive and negative charge carriers can constitute the total current in a transistor. Hence, it is named as bipolar. And why we mention as a bijunction? Because we have two junctions. So here we have a junction between emitter to base. Another junction is between base to collector. So the junction between base to emitter is known as input junction. The junction between base to collector is known as the output junction. So base to emitter junction is known as input junction. Base to collector junction is known as output junction. Now the BJT is constructed with a 3-doped semiconductor region. So we already know that what is doping. So addition of impurities. The or adding the impurities is called as a doping. Now, so how many doped semiconductors? Because I require 3 regions, hence I have 3 number of doped semiconductor devices. Now, out of those 3 doped semiconductors, two are n-type. One, the middle base or the middle region, which is the base, is a p-type material. So we already have an idea how the n-type material is formed, how the p-type semiconductor is formed by doping acceptor impurities to the pure semiconductor silicon or germanium. We have a p-type material. By doping the donor impurities to a pure semiconductor, which is a 4th group element. So we'll have the N-type material. So here there is a difference between the doping concentrations. Now, so based on that, we name this as emitter, collector, as well as the base. So heavily doped N-type material is an emitter. Lightly doped P-type material is a base. Or generally we say emitter is heavily doped, base is lightly doped, and collector is moderately doped. So it is in between the base or the emitter. So in between those, so amount of impurity concentration is in between the base and the emitter dopant impurity concentration. So emitter is a heavily doped one, base is a lightly doped one generally. So collector is a moderately doped one. And base, now coming to the regions, so the occupying regions of each semiconductor we have to discuss. So emitter is having the collector occupies. Sorry, first let me move the highest region. So collector occupies the highest region out of these two semiconductor types, base and emitter. Base occupies very less space than your emitter. Very, very less. Out of the three regions, the collector is having the highest region, the width of the region is more, where the base width is less. And the emitter is in between the base to collector. It is moderately, it is occupying the region. So this is about your hello. I'm going to give a question about this slide. Anyone can answer? So which region can occupy more space? You can answer this question. Yes, good. So collector occupies more space. And which region, next question, which region can occupy very less space compared to the all the three regions? Base, good, very good. So now I'm going to ask one more question. So which is heavily doped region? Which is heavily doped region? Yes, emitter. Yes, good. So which is lightly doped region? Base. Good. Next. Which is moderately doped? Moderately doped collector. Why we named this as a transistor? Why we named this as a transistor? Can anyone? Why we named this as a transistor? It transfers resistance from low resistance region to the high resistance region. Oh, good. Right. Next, I'll move to next slide. So now we are going to have a brief intro about the types of the transistor. So BJTs are classified into two types mainly. The first one will be NPN transistor And the second one will be PNP transistor. How to form an NPN transistor? By taking two N regions which are separated by a P region is called NPN. So now PNP transistor, how to form a PNP transistor? By taking two P regions which are separated or sandwiched between the two P regions with an N region, it is called as a PNP transistor. So now, are you able to see my cursor? So this picture will give the actual basic structure, and the down picture will give the basic electronic symbols of transistor NPN and PNP. So electronic symbols of transistor NPN and PNP. So these are the notations, or these are the symbols which we are going to utilize for representing NPN and PNP. Now, so in order to differentiate the terminals, we have provided a arrow mark. So because we have three terminals, so emitter, base and collector. Always remember the arrow which is there at the terminal is called, always the arrow is represented on emitter, and the base is your, so you have to represent that as a horizontal line, and the other terminal is nothing but your collector. So always the arrow which is represented on a terminal is called as a emitter. Now the arrow direction here indicates the original current flow. The current flow through the transistor. The direction of the flow of current. So which is denoted by the arrow mark. So in a PNP, in a NPN transistor, which is you are showing it is directed towards the emitter. Whereas here in a PNP transistor, your arrow which is coming from the emitter and directing towards to the base. So this is the original current direction in a NPN and PNP transistor. Is it clear, everybody? Right? Next, I'm moving to your next slide. So now in my next slide, already I have discussed this, I think so. So input junction is a base to emitter junction, and your output junction is a base to collector junction, is also called as a output junction. So the PN junction is in between the base and emitter is known as input junction or base emitter junction. Next, the PN junction joining the base region and the collector region is called as a base to collector region or the output junction. Now, so we have so many construction methodologies to construct your transistor. So out of that one will be the epitaxial planar or a contact method. We have a grown junction type of transistor. So now, so this is the actual basic epitaxial planar structure which denotes with a substrate. We have to take a substrate and we have to provide the etching. After etching, we have to do with the if it is an NPN transistor, we have to do with the donor impurities which occupies the host base. Then we have to provide with the acceptor impurities in order to have the base. Thereafter, we have to provide with the emitter. Now, just to look into your epitaxial planar structure of your NPN transistor or a PNP transistor, it might be. So, just to see here, the base occupies very less width than your other region. So collector is occupying more space and more area than the other two regions. Hence, emitter occupies moderately occupied with the area. Base is very small compared to the other two, where collector is having a larger space. So now, next coming to the next picture. This picture gives you this picture. So here we have a picture with a practical BJTs. Now all are three terminal devices. So one will be the cylindrical structure, one will be in the D shape. So these are some of one example I will BC107 EP bipolar is one of the example for your transistor. So silicon transistor. Now, so here just are you able to see my arrow here or a cursor? Are you able to see my cursor here, everybody? Yeah. So here, just look it over there. So there is an extra part which is denoted as, or which is known as a notch. So if we have a transistor like a cylindrical shape with a extra part which is called as a notch, and from that notch we have to move in an anti-clockwise direction. So the terminal which is nearer to the notch is your emitter, then base, thereafter the collector. So it is arranged like a water tank or a cylinder type. So the extra part which we have here, so it is called as a notch, and the terminal which is nearer to the notch is called as a emitter. So emitter terminal in an anti-clockwise direction, it will be base and collector. So these are the practical transistors picture we have in image. So next, now let me first analyze our transistor. So for the analyzation purpose point of view, so let me treat we connected two PN junction diodes. And don't think that after connecting those PN junction diodes, it can act like a transistor. So just for our understanding, we are just thinking that your transistor is connected in a PNP configuration or an NPN configuration, like two diodes which are connected in a series connection. So now this is a one PN diode, junction diode, another PN junction diode, and wherever the cathodes are connected in series, and from that terminal we are extracting a base. But don't think that this is the actual construction of your transistor, because here the dopant concentrations are different. If you connect like this, it won't work like a transistor, since its doping levels are different. So in your transistor, the doping levels for each region is different. So now let me move to our next slide. Bipolar junction transistor basics. So these two are the structures of PNP as well as the NPN transistor. Now, so PNP transistor, P type is emitter, N type base, P type collector. Now the notations which we are going to give for the emitter current is I. We have a subscript with E, so which denotes the emitter current. I, the subscript B, denotes the base current. I with a subscript C denotes the collector current. So it is a PNP or it is a NPN. The notations are same. So I is the emitter current, IB is the base current, IC is the collector current. Now let me apply the Kirchhoff's current law. Now amount of emitted current from the emitter region is equal to the summation of the base current as well as the collector current. The same manner, amount of applied voltage in between the emitter to collector is equal to amount of voltage between emitter to base as well as the base to collector. So now let I move to our next slide. So this is our just overview of your first day session. Now let me move to our present session. This is your basic transistor which we have given the biasing voltages at input junction and at the output junction. So now, so input junction is base to emitter, output junction is base to collector. And in order to protect our transistor, let me connect a series resistance which is in series with your input terminal as well as in series with your output terminal. In fact, we connected the resistor here at a base as well, because we applied a biasing voltage here. Hence, so it must be, 1 second. So it must be applied with. So here we have taken base to emitter junction is the input junction. So we have to apply a forward bias to the input junction and a reverse bias to the output junction. So our output junction is base to collector, whereas input junction is base to emitter junction. So in order to operate a transistor under active region, so we have three region of operation because we have three terminals. So we have actually four, and the last four region of operation we are not going to utilize, and so we are not going to consider that. So now base to emitter junction, forward bias, base to collector junction, reverse bias, which is active region. If input junction and output junction both are reverse bias, then it is called cutoff region. If input junction and output junction are both forward bias, then it is known as saturation. Now, the last one which we are not going to discuss or which we are not familiar is your base to emitter junction is reverse bias, and your output junction, which is base to collector junction, is forward bias, that is reverse active region. So that we are going to we are not going to utilize, and it is not considered. So we are not going to discuss about that now. So this is an example. These two configurations are, one will be the first one will be the NPN, and this is the second one will be the PNP configuration, where we have taken the emitter as a common terminal. So three terminals we have, and one of the terminal must be taken as a common. Based on that, we have three classifications. One will be the common emitter configuration. If I am taking emitter as a common terminal, if I am taking base as a common terminal, then it will be known as a common base. So if I am taking common collector, then it will be, if I am taking the collector terminal as a common terminal, then it is known as a common collector configuration. So in order to put our transistor, for this NPN or NPN, we have to apply the input junction forward and output junction reverse. Now I'm going to ask you a question. So everybody listen. So how to put the transistor in saturation? Anyone can answer to your chat box. Yes, good. Only one? Only one answered. Why you took so much of time? Right. Both junctions forward biased. Good. Next. So how to put the transistor in active region? How to put the transistor in active region? Forward bias, reverse bias. Which one will be the forward bias and which one will be in reverse bias? You have to mention that input junction must be forward biased and output junction must be reverse biased. Input junction forward biased and output good. Right. Now how many types of configurations we have? Three types: common emitter, common base, and common collector configuration. Okay, right. Next slide. So this is a basic transistor operation. Now now you tell me which type of configuration it is. Which type of configuration it is? See the image and tell me. So which I am taking common out of the three terminals? Which I am taking common out of the three terminals? Emitter. Good. So it is a common emitter configuration. So which type of transistor it is? Which type of transistor it is? I took a NPN transistor. It's an NPN transistor. Right. So now input junction is base to emitter junction. Must be forward bias. So base is P type. Hence are applied voltage or the bias voltage where you are applying at the input junction to your resistance RB, you have to apply a positive terminal where the negative terminal must be connected to the emitter because I took the emitter as common. Next, our output junction is base to collector. So that must be reverse biased, right? So collector is of N type. So in order to apply the reverse bias, you have to apply a bias voltage positive terminal to the collector terminal. Positive terminal to the collector terminal and negative terminal to the common. Negative terminal to the common terminal which you took as a emitter. So here we are applying base to emitter junction forward and base to collector junction is reverse bias. Okay, right? So now the operation let me continue in the next class. So here you have to take a test. So now I'm giving you 15 minutes of time. So you can wind up within the 15 minutes of time. And now I'm going to start that. So in the next session, let me go through your brief or the basic transistor operation. Thereafter, we are moving to the configurations. And in the configuration, we have to mention the gains of your transistor. Actually, the gain is nothing but output to input. So now I am taking here the currents as the output. So output current to input current is the current gain of your each transistor configuration. In a common emitter configuration, our input current is base current and our output current is a collector current. Hence here beta is denoted as ratio of output current to input current, whereas in common base configuration, base we are taking a common terminal. Our input current is emitter current and output current is collector current. So ratio of IC to IE is known as a current gain in a common base configuration. In the same manner, in a common collector configuration, output current is output current is IE and input current is your base current. So IC by IB is your IE by IB is your current gain in your common collector, which is known as gamma. So beta is the common base current gain, alpha is the current gain of common emitter, and gamma is the current gain of your common collector. So IE by IB in common collector, IC by IB in common emitter, and IC by IE in common base configurations. Right. So let I just introduce or will go through your brief discussion about your PNP transistor and NPN transistor in the next class. And just we're going to start a quiz now. Just attend the quiz and you can log out at 5:20. Thank you.